Today we're going to be talking about how to find the equations of the normal and oscillating planes. And in this particular problem, we've been given these parametric equations here, x equals 2 sine of 3t, y equals t, and z equals 2 cosine of 3t. And we've been asked to find the normal and oscillating planes of the curve defined by these parametric equations at the point 0, pi, negative 2. So as a reminder, I've written some equations that we're going to need. This is the equation of a plane, just the basic equation of a plane. Remember that A is the slope in the x direction, B is the slope in the y direction, and C is the slope in the z direction. We know also that we'll plug in the point 0, pi, negative 2 for x sub 0, y sub 0, and z sub 0. So we already have that. Really then, all we need to find the equation of the plane are the values for A, B, and C. And we're going to need two sets of values for A, B, and C. One for the normal plane, and then another for the oscillating plane. So how are we going to find those? Well, they're going to come from the vectors that lie in these planes. So we need the normal vector. The normal vector lies within the normal plane. So if we have that normal vector, then we can take the components of that vector and plug them in for A, B, and C. And then we need a vector that lies in the oscillating plane. That's going to come from this B of t formula here. We're going to get that vector by taking the cross product of the tangent vector and the normal vector. That vector, the result, will lie in the oscillating plane, so we can pull the components for A, B, and C from that vector. So we're really working backwards here. We have these formulas for the normal vector, the tangent vector, and this vector B of t here. What we want to do is start with the unit tangent vector, because as you can see, we're going to need this capital T of t value to plug into our unit normal vector formula right here, because we have capital T prime of t. So we really have to start with this middle formula. Well, in order to use this formula, notice that we're going to need an equation for r of t so that we can take its derivative and find r prime of t. So we want an equation for r of t, and we're going to get that by using our parametric equations that we've been given. So all we're going to do is say that r of t is equal to, we're going to transform these parametric equations into one vector equation. And each of these is just going to become the coefficient on our I, j, and k terms respectively. So we're going to say 2 sine of 3t times I plus t times j. See how we're just taking each of these and making them coefficients on I, j, and k? And then plus 2 cosine of 3t times k. And x, y, and z are always going to correspond to I, j, and k respectively. So now we have this vector equation r of t. Notice that we need, though, r prime of t for this unit tangent vector formula. So we're going to take the derivative and get r prime of t is equal to, and in this case we just take the derivatives of the coefficients in front of these I, j, and k values here. So the derivative of 2 sine of 3t is 6 cosine of 3t. The reason being, because we're going to use chain rule here, the derivative of sine of 3t is cosine of 3t. But remember then that we have to multiply by the derivative of this inside function 3t. Well, the derivative of 3t is just 3, so we multiply by that 3, so 2 times 3 here becomes 6, so we end up with 6 cosine of 3t, and then of course multiplied by I. The derivative of t is just 1, so we get 1j, or just j, and then the derivative of 2 cosine 3t is again here 6 sine of 3t, but we have this negative sign out in front because remember, the derivative of cosine is negative sine. So we'll get negative sine of 3t, but then we have to multiply by the derivative of the inside function 3. So we're going to get plus negative 6 sine of 3t. And we're going to multiply that, of course, by k. So why don't we just distribute that negative sign and simplify this? We'll get 6 cosine 3ti plus j minus 6 sine of 3t times k. So now we have a value for the derivative of r of t, r prime of t. So we can plug that into the numerator of our unit tangent vector formula. But we're also going to need the magnitude of the derivative of r of t. The way that we're going to find that, we're going to say the magnitude of r prime of t. The way that we're going to find that is by taking the square root of the sum of the squares of each of the coefficients in this derivative, which sounds more complicated than it is. All we're going to do is take the coefficient on each of our I, j, and k terms, square it, add them all together, and put them under our square root sign. So 6 cosine of 3t squared, when we square that whole quantity, we're going to square the 6 here and get 36 out in front. And cosine of 3t becomes cosine squared of 3t. So that's the square of that coefficient, everything in front of the I term. In front of j, we just have a 1, right? This is plus 1j. So 1 squared is still 1, so we get plus 1. Then we're going to add to that the square of negative 6 sine of 3t. Remember to include this negative sign. But of course, when we square it, it's going to go away anyway. So negative 6 squared gives us a positive 36. And then we get sine squared of 3t. So we just add those all together, and we put that underneath our square root sign here. And now we need to simplify. So what we want to do is recognize that we have cosine squared of 3t and we have sine squared of 3t. We can put those two terms together and then factor out a 36. So we'll get 36 times cosine squared of 3t plus sine squared of 3t, like this, and then we have our plus 1 out here. So cosine squared of 3t plus sine squared of 3t, based on our trigonometric identity, we know that that's equal to 1. So this is all just going to cancel because 1 times 36 is still 36, and you can see that we end up with then the square root of 37, 36 plus 1. So now you can see we have the two values we need. We have r prime of t here, we found r prime of t, and then we have the magnitude of r prime of t here in our denominator. We've got that right here. So what we can do is just divide this value here by this square root 37 value, and we can get a value for the unit tangent vector, capital T of t. So we'll squeeze that down here because we're going to need the room. So we have the unit tangent vector, and basically we're just dividing this value by this one, but we really don't want to distribute the square root of 37 across each of these terms yet. So what we'll just do is we'll bring this 1 over root 37 out in front, and we'll multiply that by this r prime of t value that we have here. So we'll get 6 cosine of 3t times I plus j minus 6 sine of 3t times k, like this. So really we just took this value and divided by root 37. We just pulled that root 37 out in the denominator as a fraction in front here so that we could factor it out. So now we have the unit tangent vector capital T of t, and we need to use it to find the normal vector capital N of t here. Notice that to find the unit normal vector, we need capital T prime of t, so we need the derivative of our unit tangent vector, and then we need the magnitude of the derivative of our unit tangent vector. So first let's go ahead and find the derivative. So we'll say capital T prime of t, and we're just going to take the derivative of what we found here. Well, when we take the derivative, our coefficient 1 over root 37 is going to stay out in front, so we're going to have 1 over root 37. And then again here on the inside, we're just going to take the derivative of each of our coefficients, leaving I, j, and k as they are. So the derivative of 6 cosine of 3t, remember that the derivative of cosine is negative sine, and we have to use chain rule to multiply by the derivative of the inside function. So we're going to get negative 18 sine of 3t times I. The derivative of 1, the coefficient in front of our j term here, is just 0, so that's going to go away, plus 0j is going to become 0. And then here, the derivative of negative 6 sine of 3t, the derivative of sine is cosine, so we'll get cosine of 3t, but then we have to multiply by 3, so we're going to get minus 18 cosine of 3t times k, like this. So there's the derivative of our unit tangent vector. Now we need to find the magnitude of this derivative here so that we can use it in the denominator of our unit normal vector. So we're going to say the magnitude of capital T prime of t, like this. And again, we're going to use this square root formula that we used here. So we're going to say the square root, we need to include this 1 over root 37, so we'll do 1 over root 37. We need to square that because it would have been distributed across these components, so we need to include it underneath our square root sign here. But then we're going to multiply that by the square of each of these coefficients. So negative 18 squared here is going to give us a positive 324. Sine of 3t, that whole value squared, is sine squared of 3t. And then again here, we square the coefficient on this k value here, so we'll get plus 324 cosine squared of 3t. And we'll close that off, and this is all underneath our square root sign. So when we simplify here, 1 over root 37, when we square that, we're going to get 1 over 37. So we have 1 over 37. And then we're going to factor out a 324 here. So we factor out a 324, and we're multiplying by sine squared 3t plus cosine squared of 3t. And as you can see, we looked at that before, we know that that value becomes 1, right? This is just 1 based on a trigonometric identity. So 324 times 1 just gives us 324. We know that the square root of 324 is 18. So what we're going to end up with here is just 18 over root 37 as the magnitude of the derivative of our unit tangent vector. So notice now again our formula over here for the unit normal vector. We have this derivative of the unit tangent vector, and we found that value right here. And then we have the magnitude of the derivative, which we found right here. So we just need to divide this orange value by this blue value. Okay, so that's going to give us the unit normal vector. So let's go ahead and write it here. We have the unit normal vector. Now, when we divide this orange value here by this 18 over root 37, what we're actually going to do, since we're dividing by this fraction, is we're going to multiply by the inverse. So we're going to get this 1 over root 37 coefficient, 1 over root 37. Instead of dividing by this fraction, we're going to multiply by its inverse. So we're going to flip it upside down and get root 37 over 18. These, of course, will cancel, and we'll be left with 1 over 18. So that's how those coefficients work out. The unit normal vector then is just 1 over 18 times the rest of this here, negative 18 sine of 3ti minus 18 cosine of 3tk, like this. Now we have an expression of our unit normal vector, but we need to simplify it further because notice that we have a negative 18 that we can factor out of this vector. We want to go ahead and actually leave the negative sign on the inside because sometimes that can mess with our coefficients, but we can pull out at least the 18. And when we do that, we'll get capital N of t is equal to, pulling out the 18, we'll get 18 over 18 in front, which will just be 1. So we'll just be left with negative sine of 3ti minus cosine of 3t times k, like this. Now, if we want to give ourselves some room and to simplify this a little bit further, let's go ahead and rewrite the unit tangent vector and the unit normal vector, pulling out just the components in front of ij and k, just the coefficients, removing the ij and k. So here for our unit tangent vector, we're going to get 1 over root 37 in front like this, and we're going to pull out our coefficients. So we're going to have 6 cosine of 3t, which was in front of the I, comma 1, which was in front of the j, comma negative 6 sine of 3t, and we leave out I, j, and k. So now we just have the components. And then for the normal vector, capital N of t, we'll do the same thing here. So we have no coefficient, and then in front of the I we have negative sine of 3t. There's no j term, so we've got 0 here, and then the coefficient in front of k here, we've got negative cosine of 3t. So now that we have the components of the unit tangent vector and the unit normal vector, we can go ahead and find the binormal vector, which we're going to find by taking the cross product of the unit tangent and unit normal vectors. So we're going to say capital B of t is going to be equal to, and in order to find our cross product, of course, we're going to need our matrix. So we're going to put I, j, and k in the first row of our matrix, and then in the second row, we're going to put the components of our unit tangent vector. We're going to leave this 1 over root 37 outside of the matrix, so we're just going to put 6 cosine of 3t here, which was the coefficient on I, 1 under j, and then negative 6 sine of 3t like this. And then in the third row, we're going to put the components of the unit normal vector. So again here, negative sine of 3t, 0, and negative cosine of 3t. And then we said we were going to leave our 1 over root 37 outside of the matrix, so we'll multiply by 1 over root 37. So now to simplify this, of course, remember that with a matrix, we're going to start with I, and we're going to take everything that's outside of the row and column that contains I, which is these 4. So then we're going to multiply upper left by lower right, so 1 times negative cosine of 3t. Of course, we'll put this 1 over root 37 out in front here. But 1 times negative cosine of 3t gives us negative cosine of 3t minus the lower left times the upper right. So 0 times negative 6 sine of 3t is just 0, and we multiply that by I because I is outside of this row and column here. And remember too, with a matrix like this, we put a positive coefficient in front of the I, negative in front of j, and positive in front of k always. So now we're going to subtract, because we have this negative sign in front of j, everything outside of j's row and column. So we have j here. We're going to take everything outside of the row and column containing j, which is these four here. So now we're going to do upper left times lower right. So 6 cosine of 3t times negative cosine of 3t is going to be a negative 6 cosine squared of 3t. And then subtract lower left times upper right, which is going to give us, those negative signs will cancel, a positive 6 sine squared of 3t multiplied by j. Now we're going to add to that the coefficient in front of k, and remember everything outside of k's row and column, which will be these four here. So upper left times lower right, we can see that that's going to be 0, minus lower left times upper right, which is going to be negative sine of 3t. So this negative sign will become a positive. Those will cancel. Sine of 3t multiplied by k, and we'll close our square brackets. Okay, so now we just need to simplify. We're going to get 1 over root 37, negative cosine of 3t minus 0. So we're just going to have negative cosine 3t like that. The coefficient here in front of j, we have 6 cosine squared 3t minus 6 sine squared 3t. If we look at just this part right here, these parentheses here, what we're going to do is factor out a negative 6 from there. So negative 6 times cosine squared of 3t plus sine squared of 3t, like this, because we're factoring out a negative 6, so this negative becomes positive. This is just going to become 1 here. So this whole thing, everything inside these blue parentheses here, becomes just negative 6. But of course we have a minus right here, minus negative 6, so that'll become a positive 6. So we just have 6 as the coefficient in front of j. And then for the coefficient in front of k, we just have this sine of 3t here. So sine of 3t like this, and this is our binormal vector, capital B of t. Now that we have all of this information here, we're finally ready to start building the equations of our normal and oscillating planes. What we need to do is we need to evaluate the derivative r prime of t right here. We need to evaluate this at the value of t that corresponds to our coordinate point. We also need to evaluate the binormal vector, capital B of t, at the value of t that corresponds to our coordinate point. Well, we don't know which value of t corresponds to our coordinate point, but we can find it in a couple of ways. So we just need to solve for t. Well, what we realize is that we have this parametric equation we were given here, y is equal to t. Well, if y is equal to t, and we know that we're looking at the coordinate point 0, pi, negative 2, then we know that t is equal to pi. So we're going to be evaluating at t equals pi. The other way that we can see that is by looking at our unit normal vector, capital N of t, and we see that we have this 0 value here as the coefficient on the j component, or it corresponds to the y value of our coordinate point. So those two things both tell us that we're evaluating at t equals pi. If we had been given instead x equals t and y equals 2 sine of 3t, if these two had been reversed, we would have been evaluating at t equals 0. We would have taken the x value instead of the y value. So we want to plug t equals pi into our derivative equation here, r prime of t. When we do that, we're going to get r prime of pi is going to be equal to, so now notice we're plugging it in here, we're plugging it in for t. So when we plug in t equals pi, we'll get 3 pi here. Cosine of 3 pi is going to give us negative 1, and negative 1 times 6 is going to give us negative 6. So we're just going to write our components here, negative 6. When we try to plug pi into the coefficient on our j term here, well, the coefficient on our j term is just 1. There's no place to plug in pi, so we're going to just take the component here, 1. Then when we plug pi into the coefficient on our k term, we're going to get 3 pi. Sine of 3 pi is 0. 0 times negative 6 just gives us 0. Now these are going to be the values for a, b, and c for our normal plane. So our normal plane right here, we'll find normal plane first and then oscillating. But our normal plane, we're going to take these three values for A, B, and C, and we already have here x sub 0, y sub 0, and z sub 0. So the equation of our normal plane is going to be negative 6 times x minus 0 right here, plus here for b we get 1, so we have 1 times y minus pi, which we take from our point, plus 0 here for c times z minus a negative 2, so negative 2, and we set that equal to 0. So then when we simplify, we're just going to get negative 6x plus y minus pi. This whole thing goes away because it's 0. That's going to be equal to 0. And then, of course, we can solve this for y, and we can say y is going to be equal to 6x plus pi. And this is the equation of the normal plane. Now, if we want to find the oscillating plane, the first thing we need to do is take this same pi value and plug in t equals pi to our binormal vector here for t. So what we'll get then is b of pi, because we're plugging pi in for t. So b of pi is going to be 1 over root 37. And then here, cosine of 3t, well, that's going to be cosine of 3 pi, which is a negative 1. But then we have this other negative sign, so negative 1 gives us a positive 1. There's nowhere to plug t in here, nowhere to plug pi in here, so we just get 6. And then sine of 3 pi is going to be 0, so we get 1, 6, 0. Now these values here are going to be the values a, b, and c that we plug into the equation of the tangent plane to find the equation of the oscillating plane. And we actually, when we plug these back into the equation of the plane, and we plug in the point P for x0, y0, and z0, we actually don't even have to include this 1 over root 37 value, because think about it this way. If we distributed this 1 over root 37 across the 1, 6, and 0, we'd have 1 over root 37, 6 over root 37, and 0 over root 37, or just 0. We'd plug those values in for a, b, and c, but then to simplify the equation, we'd multiply both sides by root 37 to cancel it from the denominators of a, b, and c, and of course over here we'd have 0 times root 37, which would just be 0, so that's going to disappear anyway. So if you ever have this coefficient factored outside of a, b, and c, you can actually just ignore it and we'll just plug in a, b, and c. So then we're going to go ahead and say that the equation of the oscillating plane here is going to be a, which in our case is 1, times x minus x sub 0, which is 0, then plus b, which is going to be 6, so plus 6 times y minus y sub 0, which is pi, plus c, which in our case is 0, times z minus z sub 0, which is a negative 2, so z minus a negative 2 is z plus 2, and that's going to be equal to 0. So now we just simplify, and here we get x plus 6y minus 6 pi. The 0 is going to cancel this whole term, so it'll just be equal to 0. And then just to keep things simple, we'll go ahead and add 6 pi to both sides, and we'll say x plus 6y is equal to 6 pi is going to be the equation of the oscillating plane. And that's how you find the equations of the normal and oscillating planes.